Hi, and welcome to our last lecture for college algebra. So congratulations, if you made it this far, then you know college algebra, hopefully. Section 5.4, exponential and logarithmic equations. And we're just going to be learning how to solve both exponential and logarithmic equations. They're in this same section because, remember, they're inverses of each other. So since they're inverses of each other, we use logs. We use logs to solve exponential functions sometimes, and we use exponential functions to solve log functions sometimes. So let's see how this is going to go. So just as a review, we already learned most of this stuff. If the equation can be written in the form b to the u equals b to the v, then we know that u has to equal v. Okay. If it cannot be easily written in that form, then we use that. So this is the new part. We use the logarithmic property of equality to take the log of both sides. And usually we're going to use either base 10 or base e, because if we want an actual answer, that's what we can use our calculators to find it if we use 10 or e. Most calculators do not have anything other than those two functions. There are some calculators that do have different bases, but probably not, they're not allowed in this class anyway, so I wouldn't worry. Use the power rule of logs to bring down any exponents and then solve for a given variable, okay? And I'll go through step by step with you. So we start here, and when I look at this, I say, well, let's see. I know 3 can't be reduced any. I'm looking at the bases. The first thing I'm going to do is I'm going to look at the bases to see if I can make the bases the same. Because if I can make the bases the same, then I can equate the exponents, right? Remember that? I think that was 5.1. So, well, I know 27 is 3 to the 3rd power. If you don't know that, you can just start factoring 27 using a factor tree, and we can see that 27 is the same as 3 to the 3rd. So I'll just write it like this. I'll go step by step. Right? So there's nothing to do over on the left side. I already have my base. But on the right side, I want to bring that base into the numerator. If you remember how to do that, we just say that's the same as 3 to the minus 3 power times 2x plus 1. And then now we use our multiplication because we have a base to a power to a power. So this is 3 to the power of negative 3 times 2x plus 1. I really am going step by step here. I'll do it on the same line. I'll distribute that negative 3. So I get negative 6x minus 3. Okay. So I'm really actually equating this to this. So my bases are the same, which means I can just take my exponents and say they're equal to each other now, right? So I get, let's see, I'll add 6x to both sides. And at the same time, I can add 1 to both sides. And then we'll see, this becomes 7x. The 1's cancel, equals, again, this minus 6x and plus 6x cancel, and I get minus 2. And that means I'll divide both. So if I have 7x equals negative 2, divide both sides by 7, and I end up with x equals negative 2 sevenths. And that would be my final answer for this. Well, actually, solve each equation for part B. Oh, for part B, round to 4 decimal places. So for part A, we're done. Okay. Part B, okay, so now we don't have a common base and we can't make a common base because 7 is 7 times 1 and 4 is 2 times 2. And so that's not going to help me. Once I notice that, what I really need to do is take the log of both sides. And again, it is your choice. I'm going to use natural log. It doesn't matter which log you use. So I start with taking the log of both sides. And I'm taking the natural log, obviously. Okay. And now I can use my log rules. Once I have a log function, I can use my log rules. So I'm going to use my power rule because I want to be able to solve for x, and x is in the exponent. So I'm going to change, I'll do it like this. So I'm going to change this to x plus 3. Remember to put this in parentheses because it's times this whole natural log of 7 equals, and again, in parentheses, 2 minus x times the natural log of 4. Now remember, the natural log of a number is a constant. Even though I don't know what the answer is, it's still a constant. So if I want to solve for x, pretend it is 7. The first thing I would have to do is distribute, right? Because this and this are both values. Okay, hopefully that makes sense. So the first thing I'm going to do is I'm going to distribute. So I say my first term is x ln of 7 plus 3 ln of 7 equals 2 ln of 4 minus x ln of 4. So all I did is multiply each term. I multiplied x plus 3 times ln of 7, and I multiplied 2 minus x times ln of 4. And now I have this new equation. And this and this are both constants, because constant means that there's nothing that's going to change. I could type that into my calculator 100 times and I'm going to get the same answer every time because they're just a value, okay? But the value is a fraction that's kind of long, so I'm going to try to wait until the very end to use my calculator, okay? So the next thing I'm going to do is I'm going to get all the, what do we normally do? We'd get all the x's on one side because I want to solve for x, and everything else on the other side. So I'm going to add this x ln of 4 to both sides. And let's see, I hope this doesn't confuse you. That's okay, I'll wait. So I get x ln of 7 plus x ln of 4 plus 3 ln of 7 equals 2 ln of 4. And then I can subtract this constant from both sides, which gives me x ln of 7 plus x ln of 4, these cancel, equals 2 ln of 4 minus 3 ln of 7. Okay, and I think what we'll do instead of squishing it in here is I'll make a new slide. And let's copy our last. Okay, I guess they're not gonna let me copy just one piece. So let me copy this. And we'll paste it. And we'll get rid of a bunch of it. Let's see. So I don't want any of this. That's on the previous page. That's the only reason I'm getting rid of it, because I want to start with a fresh page here. Okay, let's move this up. Let's see. How can I get this? Let's see, let's try this. Nope, that's not going to work. Oh, okay. That actually might have worked better. Let me change this to an ln. And this to an ln. And let me just make sure that this is correct. So I have x ln of 7 plus x ln of 4 equals 2 ln of 4 minus 3 ln of 7. Okay, perfect. So that's where we're going to start. Okay. And these are all in parentheses. Okay. So I want to solve for x, but I have x in two places, right? I have an x here and I have an x here. So what I'm going to do is I'm going to factor out that x. And when I do, I get x times ln of 7 plus ln of 4 equals 2 ln of 4 minus 3 ln of 7. Okay. And then I can divide both sides by ln of 7 plus ln of 4. Because remember, this is just a number still. Okay, and then these cancel, and I end up with x equals 2 ln of 4 minus 3 ln of 7 divided by ln of 7 plus ln of 4. Now, if you feel really comfortable with your calculator and you want to just put it in like this, you can. Or if you feel more comfortable with the log rules, we could do this. We can start by saying this is the same as ln of 4 squared, using my power rule, minus ln of 7 cubed, divided by ln, and then I have a plus between them, so I can say 7 times 4, right? Now this is equal to, and I can make a fraction here, right? I can say this is equal to ln of 4 squared divided by 7 cubed over ln of 28. I don't know if this is helpful or not, so I'll just keep going. This is 16 over 343 divided by ln of 28. So now it's a little bit easier to put these numbers in the calculator instead of putting all those numbers. But if you like, you can put all these values before I started combining them together. And when you do that, let me just check here, make sure I'm correct. I'm just going to pause it for a second so you don't have to wait for me. Okay, so that is equal to rounding to, because remember it said here, to round to the 4 decimal places. So if I round this to 4 decimal places, I get negative 0.9199. And that is what x is equal to. Okay. So this is getting a little more complicated, I understand. Next equation, it says solve these and round to the nearest, round to 4 decimal places. Well, again, I have this e. So, but the x that I'm trying to solve for is in the exponent. So again, I have to use my log rules. But I don't want to use my log rules first. What I want to do first is just get e by itself. So the first thing I want to do is divide both sides by 25, because that way I have e to the x minus 5 equals 17 over 25. Now, when I take the log of both sides, and which log should I take? I should take the natural log because e is my base. So I'm going to take the natural log of both sides. So I have the natural log of e to the x minus 5 is equal to the natural log of 17 over 25. And now I can use my power rule. So I have x minus 5 times ln of e is equal to ln of 17 over 25. Ln of e, we've said a bunch of times, is 1. So I end up with x minus 5 is equal to the natural log of 17 divided by 25. I can add 5 to both sides. And I get x equals the natural log of 17 divided by 25 plus 5. And now this I can put in my calculator. And if I do, I get, oh, super sorry. I don't know what I just did. Hold on a second, because I can't see anything but my background. Hold on. Oh, where did my meeting go? Oh, okay. There we go. Hopefully this worked. I didn't lose everything. So now the answer to that, if we put it in your calculator, is going to be approximately 4.6143. That's a 4. Okay, so that's how you do this, because you always have to look to see what I have to do. And because the x is in the exponent, I have to take the log because I need to use the power rule to get it down into the base. Okay. Okay, now for this one, first thing I really want to do is I want to combine, because remember we have the rule for exponents that says if we have a base to a power times a base to a power, we add exponents. So that's what I have. The bases are the same and the exponents are different. So I just need to add them. So I get 2x minus 1 plus x plus 4 equals 11. I combine like terms in the exponent and I get 3x plus 3 equals 1. But now what am I going to do? Now I want to take the natural log of both sides, right? I'll just write over that. I want to take the natural log of both sides, because either way, either I can use the cancellation property or I can use the power rule, and I get 3x plus 3 equals the natural log of 1. Oh, the natural log of 1, we know what that equals. We've seen that many times, haven't we? It's equal to 0. So we get 3x, this is equal to 0. The natural log of 1, any log of 1 is always 0. So we get this equals 0. Oh, except, let me rephrase that. Okay, sorry about that, guys. It's not 1, it's 11. I just didn't write the 11. So we have 11, we have 11. We have the natural log of 11. Now we're going to subtract 3 from both sides. And we get 3x is equal to the natural log of 11 minus 3. Divide both sides by 3. And I get, so I'm going to come up here, I get x equals the natural log of 11 minus 3 over 3, which is equal to approximately negative 0.2007. Okay, so you can't do anything with the log on the left unless you just have e. If you take the natural log of that whole thing, it's just going to complicate matters. And you're still going to have to combine them into one term. So I would do that first. Hopefully that's clear. Again, we have the same properties. They're just repeating them here. There's nothing new, exactly what we said before. So let's go and solve another equation. So here, well, notice I have the log base 5 on both sides. So that's kind of good. Really what I need to do is if I use my power rule and I make this squared, then notice I have log base 5 of x minus 1 squared equals log base 5 of 64. And now I have the log of u equals the log of v, because I could say u is equal to x minus 1 squared and v is equal to 64. So I can get rid of the logs and I can say x minus 1 squared is equal to 64. And honestly, I could do a lot of things here, but the easiest thing to do is take the square root of both sides. So I'm going to take the square root of both sides, which gives me x minus 1 equals plus or minus. Don't forget, when we take the square root, we have to add that plus or minus, and the square root of 64 is 8. So now I have two possibilities. I have x minus 1 is equal to 8, or x minus 1 is equal to negative 8. Which means x equals 9 or x equals negative 7. Okay, those are my two possibilities, right? Well, what's the first thing? What's the last thing I do? Not the first thing, but the last thing. I take this number and I plug it back into my original equation. And when I do, x is 9, I get 9 minus 1 is 8. It's positive. So check, that is a solution. But when I plug in x equals negative 7, I get negative 8. And we cannot take the log of a negative number, which means that the only solution here is x equals 9. Okay? Don't forget that part. You will get it wrong otherwise. Okay, so solving logarithmic equations. First, we want to determine the domain of the variable, use the properties of logs to combine all the logarithms and write as a single log, eliminate the logarithm by rewriting the equation in exponential form, solve for the variable, and check for extraneous solutions. So that is basically our marching orders. So here, let's see. Determine the domain of the variable. Well, the domain, if you remember, is I have this here, the 2x minus 1 has to be greater than 0. So I add 1 to both sides. I get x has to be greater than 1. Divide both sides by 2, and I say x is greater than 1/2. So as long as my solution comes out to x is greater than 1/2, I'm in good shape. Second step, use properties of logs to combine all logarithms. Okay, well, we can use that rule, that little trick, I guess we could say, where we said 4 squared is equal to 2x minus 1. So I'm going to rewrite that as 4 squared is equal to 2x minus 1. 16 is equal to 2x minus 1. I add 1 to both sides. I get 17 is equal to 2x. Divide both sides by 2. I get x equals 17/2, which is really the same as, you can probably put it in as a fraction, but if you like, this is 8.5. 8 is 16, so I have a half more. That is in the domain, so we're in good shape, right? Then I want to check if that's an extraneous solution. Well, it can't be an extraneous solution because it is greater than 1/2. So my final answer, I think they probably want a fraction, so the answer would be 17/2. Okay? And here we have our last one. So this is actually the argument for the entire thing. Again, we can use our arrow thing. So 2 to the 5th is equal to x plus 10 times x plus 6. So let's rewrite that. 2 to the 5th is equal to x plus 10 times x plus 6. Okay, well, we know how to solve that, right? First thing we have to do is figure out what 2 to the 5th is. And 2 to the 5th is 32. So we have 32 is equal to x plus 10. So we're going to FOIL that. We get x squared plus, I'll do it slow, 6x plus 10x plus 60. So, and remember, whenever we do this also, we have to make it equal 0. So while I'm doing it, let's subtract 32 from both sides. And we get 0 equals x squared plus 16x plus 28. Okay? And now we want to factor this. So if you're not very good at factoring, you could always make yourself a table. So 28 is 1 and 28. 2 and 14. 2 and 14, if I add those together, I'm going to get 16. So that is my factors. So I get x plus 2 times x plus 14, which means that x is equal to -2 or x is equal to -14. Well, if I put x equals -2 into my function, everything is still positive, right? -2 plus 8 is, -2 plus 10 is 8, and -2 plus 6 is 4. So that works. But this -14, it's going to give me a negative value. So that does not work. So if I want to know what my answer is, my answer for this whole equation is x equals -2. Well, we didn't find the domain first. The domain for that is a little bit harder to find. So if you know what, let me show you how to find the domain because we have a few more minutes. So why not? Let's do that. Probably doing it first is helpful, but even if you do it after the fact and just plug it in, it's fine. However, let's do it because I know you do have some questions that from previous that ask you about the domain. So let's do it. Well, I already have it factored, so that's a little helpful. I have x plus 10 times x plus 6 has to be greater than 0. Okay, remember that has to be positive. So what most people want to do here is set each one of them greater than 0 and solve individually, but you can't really do that. You have to actually, there's two ways to do it. I'll do it the way that you probably will like better first, and then I'll show you another way. So we have a number line. Here's my 0. And here we're going to have, if we set it equal to 0, we have two zeros, one at -10 and one at -6, right? So we know it can't be -10 and we know it can't be -6. And the reason I'm doing that is because I want to find, I have these intervals now, right? So what the best thing to do here is to just plug in values on each interval. So for example, when I'm over in this interval here, less than -10, so I can plug in x equals -11, right? When x equals -11, I get -1 times -5, yes, which is equal to a +5. Or I can just say, when I plug in -11, I get a negative times a negative, which is a positive. The numbers are not really as important as the sign. So I know I have a positive number over here, okay? Then let's pick some value in the next interval, which is between -10 and -6. So let's pick x equals -7. So when I plug it into my equation, I get +3 times -1, or I can just say I have a positive times a negative. The numbers are not important. What's important is that I know it's negative in this interval. And then lastly, I'll plug in something on my last interval, which is, because those zeros broke up the number line. And when I do the next thing I do, you'll understand why it breaks it like that. So here I have x equals, well, I just need anything bigger than -6, right? And the easiest one's going to be 0. So when it's 0, I get 10 times 6, which is 60, which is positive, or I get a positive times a positive, which is a positive, which means here it's also positive. So now I can see my domain. My domain is, I'll write it up here. My domain, well, everywhere it's positive, right? And I took out the 0, so I don't include -10 and -6. So I can say I go from -infinity to -10. Union, I can't use anything between -10 and -6, but I can use anything greater than -6, -6 to infinity. So that's the domain of that log function. So the other way, if you understand this way, this is the way I would probably do it for at least things like this, where we have a quadratic, because I have a quadratic. When I multiply that together, I'm going to get a quadratic equation. So let's copy this to the next slide. We can paste it. Okay, so another way, if you feel very comfortable with graphing parabolas, well, we know this is positive, and we know we have a 0 at -10, and we know we have a 0 at -6, right? And I know this opens up. So if I were just going to sketch the graph, it doesn't really matter much more than this. I sketch the graph, and everywhere that this graph is above the x-axis, y is positive, or this is positive, right? So from here up and from here up, my y values are positive. I'm not talking about my x values. I need the thing that when I multiply these together, it's got to be greater than 0. And that means that the y has to be greater than 0. So looking at this, I can see that from negative infinity all the way to -10, not including, we can't include -10 because that's 0 and we can't take the log of 0, union, and we have to leave out all this here because this is all negative. Y is negative there. And then we can go from -6 to infinity. And that for me is a lot easier, especially when it's a quadratic, because I don't have to just plug in numbers. So we should have the same domain. Let's just look. Perfect. Same thing, right? All right. And so we found our solution. We found everything that's extraneous. Did we? Where did we do it? Oh, here we did it. It's equal, so x equals -2, and -2 is right here, which is in the domain. And that concludes not only 5.4, but the entire college algebra course. Congratulations. Thank you for watching. I hope you had a nice semester, and maybe we shall meet someday. Bye.